name is Erica Copeland, and today we're going to be discussing how to balance chemical reactions, and then we're going to be talking about double displacement reactions. In specific, we're going to discuss precipitation reactions. So with that said, let's go ahead and get started. So I've written this chemical equation on the board where we have ethane reacting with dioxygen to produce carbon dioxide and water. Now, as you can tell, we do not have the same number of each atom on both sides of the equation. For instance, on the reactant side, we have 2 carbons, whereas on the product side, we only have 1. Our goal when it comes to balancing is to have the same number of each atom on both sides of the equation. The very first thing that I did was to write each element down on the reactant and product side in a symmetrical way so that it's easier for me to keep track. So let's go ahead and now identify the quantity of each. On the reactant side, we have 2 carbons. I'm going to go ahead and write that down. And on the product side, we only have 1. Then looking at hydrogen on the reactant side, we have 6. And on the product side, we have 2. Now on to oxygen. On the reactant side, we have 2. And on our product side, we have oxygen here and here. So I'm going to write them separate and then add them so that it's easier for me to keep track. So again, we have 2 plus 1. That equals 3. Now when you get started, I recommend that you start with a molecule that has multiple elements so that it's easier for you later on. So given that, we're going to go ahead and get started with ethane. So over here, we have 2 carbons and just 1 over here. Like I said, our goal is to have each atoms match in numbers on the reactant side and the product side. So we have 2 versus 1. You ask yourself, 1 times what is going to equal 2? And that's a pretty easy one, right? 1 times 2 is going to equal 2. Notice how I place a coefficient in front of this compound. When I do that, that's also going to affect not only this carbon, but whatever comes after. So we have also over here oxygen being affected. So instead of 2, now we have 2 times 2, which equals 4 on that side. But now remember, we still have that one. So we have 4 plus 1, we have 5. Then we have hydrogen, 6 over there on the reactant side versus 2 over here on the product side. So you ask yourself, 2 times what is going to equal 6? And the answer will be 3, right? 2 times 3 equals 6. So again, I've placed this coefficient here, and not only this hydrogen is impacted, but also this oxygen. So now we have 3 oxygens as opposed to the initial one that we had over here. But we have 4 over there, so 4 plus 3, now instead of 5, I have a total of 7. Lastly, I have 2 oxygens over here on the reactant side, and on the product side, I have 7. So you ask yourself, 2 times what is going to equal 7? And the answer is 3.5. Right? Now, we have an issue. And the issue is that we have a fraction. And we don't really want to say that we have 3.5 molecules reacting. Instead of that, you want to have whole molecules, not half molecules. So what can we do to make this 3.5 into a whole number? One way to think about it is that 3.5 is the same as 3 and 1/2. This 3 is already a whole number, so let's go ahead and focus on this fraction. If we have 1/2, what will we have to do to it so that it becomes a whole number? And the answer to that will be to multiply it by its inverse, which will be 2 over 1. And we can all agree that 2 over 1 equals to 2. So in conclusion, every time that you have a fraction, you have to go ahead and multiply that molecule by 2. But you cannot just go ahead and multiply this molecule by 2 and call it a day, because whatever we do to one molecule in a chemical equation is going to impact the whole chemical equation. So if I multiply this by 2, I also have to multiply everything else by 2. Again, if we have a fraction, we have to multiply the whole chemical equation by 2. So let's go ahead and do that. We had 1 ethane, so 2 times 1 is going to make it into 2. We had 3.5 dioxygen, so 2 times 3.5 is going to equal 7. Then we have 2 carbon dioxide, so 2 times 2 is going to equal 4. Then we have 3 waters, so 2 times 3 is going to equal 6. And we're done. Now we're going to be discussing double displacement reactions. A double displacement reaction is when the reactants in a chemical reaction switch their cations and anions. A cation is a positively charged ion, and you can remember this because the word cation has a T that resembles a positive sign. Also, anions are negatively charged ions, and you can remember this because the word anion has a lot of N's for negative. If one of the products in a double displacement reaction is insoluble, that means that that product will be in the solid phase and would create a precipitate. Therefore, that's what we would call a precipitation reaction. I have written an example on the board, and the very first thing that we're going to be doing is figuring out what the charges are for each of the ions. So first off, what you see over here is the final chemical formula. For us to figure out what the charges are, we will have to go one step back, and we will take this 3 right here, and we will go up and across, and that would symbolize the charge of iron. Then we will take the number right here, which there is none, which means that it's 1, and we will go again up and across, and that would symbolize the charge of nitrate. So first off, let me go ahead and write them separate. And again, like I said, we're going to take this number, and we're going to go up and across, and that's going to be the charge for iron. Then we're going to take this number, like I said, there's none, so that means it's a 1. And again, we're going to go up and across, and that's going to be the charge of nitrate. So we have positive 3 and negative 1. We should always write the cation, so the positively charged, first, and then the anion, the negatively charged, second. Then after we did this first one, let's go ahead and do the same thing with sodium hydroxide. So again, the number over here will go up and across, and that will be the charge of sodium. And the number right here will go up and across, and that will be the charge of hydroxide. Also, something to note is that you were supposed to memorize the charge of hydroxide, and you were also supposed to memorize the charge of this polyatomic ion, nitrate. But nonetheless, there's nothing there, so that means it's 1. And we will go up and across, up and across. I will write them separate. And always the positive first and the negative second. After you do this, you're going to take the positive of the 1, so the cation, and the negative of the other reactant, so the anion, and you're going to write them next to each other. So let me go ahead and do that. And I'm going to be doing that with the charges that we've already found out. So 3 plus and negative 1. After you do this, you're going to take this charge and go down and across. Take this charge and go down and across. So your final product is going to be this. This one will go there, so we already said we don't write the 1. And this 3 would go here. And because this hydroxide is a polyatomic ion, we need to have those parentheses in place. That will be how we find product number 1. Then, we're going to figure out what the second product is. Again, we would take the cation of one of the reactants with the anion of the other reactant. And then what we want to do is write them next to each other. Again, we write the cation first and the anion second. So we have sodium and we have nitrate, and I'm going to also be writing the charges. Then, same thing. You will take this and go down and across, take this charge and go down and across, but because it's 1, we don't really write them. So the final product is going to be sodium nitrate. After we do this, we're going to go ahead and balance it. I went ahead and I wrote everything down on the reactant side and the product side like we did in the very first example, and I kept the polyatomic ion together. Because if you look at it, right, the polyatomic ion, nitrate right here, it still remains nitrate over here. So the NO3 still is together. So there's no reason for me to really split it up. Now, to get started, let's go ahead and count what we have on each side. So iron, we just have 1 on the reactant side, and on the product side, we have 1. Nitrate, we have 3 on the reactant side. And on the product side, we just have 1. Sodium, we have 1 on the reactant side, and we also have 1 on the product side. Hydroxide, we have 1 on the reactant side, and we have 3 on the product side. So we have iron 1 and 1, it's matching. Nitrate 3 versus 1. So again, you ask yourself, 1 times what is going to equal 3? And again, that's easy. It's going to be 3, right? 1 times 3 will equal 3. So I'm going to take the 3 and write it over here. Now this becomes 3. And because we have written this coefficient, now it's going to also impact the sodium. So we have now 3 sodiums here. So 3, 3, now we have 1 versus 3. So again, you ask yourself, 1 times what is going to equal 3? The answer is 3. So I'm going to go ahead and write 3 over here. And now this sodium will become 3. And again, because I've written that coefficient there, is not only going to impact this sodium, but also this hydroxide. So we have 3 over here as well. And now we are done balancing because we have 1 and 1, 3, 3, 3, 3, 3, and 3. Now that we're done balancing, let's go ahead and use the solubility rules to figure out the physical states of both the reactants and the products. So let's go ahead and take a look. We have iron 3 nitrate. The rule says that nitrates are soluble, and that's going to be rule number 2. So since it's soluble, I'm going to be writing AQ. Over here we have sodium hydroxide. Sodium is in group 1, and it says that group 1 salts are going to be soluble. That's going to be number 1 in your paper. So we're writing AQ. Then we have iron 3 hydroxide. So all the salts of hydroxide are going to be insoluble except for those of group 1 or barium, calcium, or strontium. That's going to be the rule number 6 in your paper. And because we don't have any exceptions applying right now over here, this will be insoluble, and therefore I'm going to be writing an S for solid. Then we have sodium nitrate, and we've already said that group 1 is going to be soluble and also all salts of nitrate. So I'm going to be writing an AQ. That's it for that. Let's do another example. Alright, so here we have our second example, and what we're going to be doing is figuring out what the charges are, just like we did in the previous example. So first off, I'm going to go ahead and write them separate. Then after you do that, you're going to take this number and you're going to go up and across. And that's going to be the charge of strontium. And remember, we write the cation first. Then the number that we have here, we're going to go up and across. There's no number, so we said that when there's no number, it's a 1. So then we have nitrate. Then we're going to be doing the same thing with the second reactant. We're going to write them separate. And then I'm going to take this number and I'm going to go up and across, and that's going to be the charge of phosphate. It's written second, so that's going to be our anion, so make sure that you write a negative charge. And then we're going to take the number here and go up and across, and that's going to be the charge of potassium. There's nothing here, so that means that it is a 1. Make sure that you're not taking this 4 to go up and across, because this 4 is part of phosphate. It is not telling us how many phosphates there are. It's just simply saying that there are 4 oxygens in a phosphate molecule. So make sure that this 4 is not going up, because it is not a charge, okay? It is not a representation of how many phosphates there are. We can see over here that there's just 1 phosphate. That's why I'm taking this number, and that's the number that I'm pulling up and across. So that's what I did. After you go ahead and you do that, you're going to write the cation of one of the reactants next of the anion of the second reactant. And I'm just going to be writing them next to each other. And I'm going to also be writing the charges that I just found out, right? After you do this, you're going to take this number and you're going to go down and across. And you're going to take this number and you're going to go down and across. So our final chemical formula for this first product is going to be this. Make sure that you're writing the parentheses, because phosphate is a polyatomic ion. And then we have the 2 going down, so the 2 goes here. So that's our first product. To figure out our second product, we're going to be doing the same thing. You're going to be taking the cation of one of the reactants with the anion of the other reactant, and we're just going to be writing them next to each other. And we're going to be writing them with the charges that we've already found out. And then I'm going to take these charges. I wanted to keep the same color. And I'm going to go down and across, but because they're 1, we don't write them anyways. So our final product is going to be this. So now that we figured out what the products are, let's go ahead and balance this chemical equation. Now we're going to go ahead and balance it. So the very first thing that I did was to write each of the ions out of both of the reactants and the products, so that it's easier for me to keep track. So then I'm going to figure out how many there are of each. So on the reactant side, we only have 1 strontium. And on the product side, we have 3. Nitrate. On the reactant side, we have 2. And on the product side, we have 1. Potassium. On the reactant side, we have 3. And on the product side, we have 1. Phosphate. On the reactant side, you have 1. And on the product side, you have 2. Now we want to make sure that all of the numbers are matching. So let's go ahead and get started with strontium. We have 1 on the reactant side and 3 on the product side. So you ask yourself, 1 times what is going to equal 3? The answer is 3, right? 1 times 3 equals 3. So I'm going to take this 3 and place it over there. Once you do that, you're also impacting this nitrate right here. So instead of 2, now we have 3 times 2, total of 6. And now we have 3 over there. So again, I added this 3 here because 1 times 3 equals 3. So now our strontium is 3, but by adding that 3 there, we have changed how many nitrates we have. We had 2, so now we did 3 times 2, which is why we have 6 over here. Next, we have 6 again of nitrate on the reactant side versus 1 on the product side. So you ask yourself, 1 times what is going to equal 6? And the answer is 6. So I place a 6 over there. Now this is 6. But notice how it's also in front of the potassium. And for that reason, we've impacted potassium as well. So instead of 1, now I have 6. So now we have 3 versus 6. So you ask yourself, 3 times what is going to equal 6? And the answer is 2. 3 times 2 equals 6. So now I'm going to place 2 here. This is 6. But now because that 2 is there, it's also impacting our phosphate. So instead of 1, now we have 2 times 1, which equals 2. So a final look, we have 3, 3, 6, 6, 6, 6, 2, 2. We're good. We're done with that. Now let's go ahead and look at the solubility rules. To write the physical states, let's go ahead and look at the solubility rules. For reactant number 1, we have nitrate, and all salts of nitrate are going to be soluble. Therefore, I'm going to be writing an AQ for aqueous. Then, reactant number 2, we have potassium, which is in group 1, and all salts of group 1 are going to be soluble. So, I'm going to be writing an AQ for aqueous. Over here, our first product has phosphate, and all salts of phosphate are going to be insoluble except those with group 1. And strontium is not in group 1, therefore this product right here is going to be insoluble, and to symbolize that, I'm going to write an S for solid. And then lastly over here, our last product, we have potassium and nitrate. Potassium is in group 1 and therefore it's going to be soluble, and on top of that we have nitrate, which is also going to be soluble. So I'm going to be writing an AQ to symbolize that. And we're done with that. One last thing that I wanted to point out is that iron, copper, and chromium are all transition metals. So you have to be careful when it comes to figuring out what the charges are for these elements. So first off, in our example previously, we had iron 3 nitrate. So with a chemical formula like this, it's easy to go one step back and take this number and go up and across, and this number and go up and across. But what if we had something like this? And you're supposed to figure out what the charge is. You would then go ahead and take this number and go up, and this number and go up, but that is not going to work out. You should know that sulfate has a -2 charge. This is one of the polyatomic ions that you were supposed to know. So because sulfate has a -2 charge, technically you will take that and it will go here. Because you're not seeing that 2 here, it means that it must have gotten crossed out. So in order to cross a -2, think of what number you need. If you said +2, you're correct. Because then you will have this number go there, this number go there, and you end up with this. Because these two numbers, right, a 2 here and a 2 here would then cross out. If this confuses you, make sure that you go over all of the polyatomic ions that you were supposed to memorize. Because if you have memorized sulfate, you know that it has a -2 charge, and if we were given this in the blue and you don't see that 2 there, that means that this iron charge must have crossed it out. One way to figure out how to do it, if you're a little bit confused, you might want to take it one step at a time. And you might have wanted to go ahead and try +1 first. So you would take this number and it will go there. You will take this number and it will go here. And you would end up with this. That's what you would have if you had iron 1. If you had iron 2, then this becomes 2. This goes down. You write the parentheses. The 2 goes there, but because it's the same number, like we mentioned before, it will cross out. If it was a +3, then you would take this number and it will go here. So you write the parentheses, and there's the 3. And you would take this 2, and it will go down there. So just take your time when you're figuring it out. Every time you have iron, copper, and chromium, because they're transition metals, you have to have Roman numerals for the charges. If you have silver, it exists as a +1 charge, so it's always going to have this +1 charge, and therefore a Roman numeral is not needed. That was all for now. Thank you guys for watching, and I'll see you in the next video.